Ever think about how easily you learn new stuff? Like you hear a song once and boom, you know it. Or your car's acting up and you're like, wait, I've seen this before? We're always making connections, finding patterns. But how do we get machines to learn like that? Like we do. It's kind of like a mystery we're going to try and solve today in our deep dive into analogizers.
Yeah, it's a whole world where algorithms learn by basically copying similarities, kind of like Sherlock Holmes, right? Using old cases to crack a new one.
Oh, that's cool. So how do these analogizers actually learn, from just being similar to something else?
Okay, so picture a map, right? With towns all over it. Each town's either in Pozistan or Negaland. You got a new town, where does it belong? Well, you'd look at the closest towns, right? That's nearest neighbor in action.
Yeah.
This algorithm, it just checks who's nearby to classify new data points.
So like a super high-stakes game of Guess Who, but with maps.
Exactly. And the cool part is it's simple. No building crazy models. It just remembers stuff and compares. That's what they call lazy learning. But hey, it works a lot of the time.
Lazy learning. I'm starting to like these analogizers already. But how does this work for the complicated stuff? Like when Netflix recommends movies.
Ooh, now that's where it gets even cooler.
Right.
Let's say we both love the same movies, and we always give them the same ratings. Chances are we'll agree on other movies too, right? That's collaborative filtering. It's like analogizing, but fancier.
So Netflix is playing matchmaker with our movie tastes, connecting us based on what we like.
You got it. And they even weight those similarities, weighted nearest neighbor. Basically, closer matches matter more, so the recommendations get even better.
Wow. So we've seen how simple comparisons can do a lot, but can analogizers handle tougher situations, where the lines between things are kind of blurry?
Oh, absolutely. That's where support vector machines or SVMs strut their stuff. Picture a minefield. Each mine is a data point. To get through safely, you'd want the widest path around those mines, right? That's what an SVM does, finds that boundary. It's called a hyperplane, and it separates the data with the biggest margin possible.
So SVMs are like careful little robots navigating a minefield of data.
Yeah. Precisely. But what if the data isn't so neat and tidy? What if it's all curvy and clustered?
Good point. Real-world data is messy. How do SVMs deal with that?
That's where they really shine. They use these things called kernels. Basically, they transform the data into higher dimensions. So imagine taking a 2D parabola and making it a straight line in 3D. It lets SVMs find those straight boundaries, even in crazy complex data.
Well, it's like bending reality to make the problem easier. So SVMs can handle those crazy patterns while still being super safe.
Exactly. And it shows that simpler isn't always better. SVMs can have tons of parameters, but they avoid overfitting because of that margin thing.
Yeah. It really shows how smart design can make a difference in machine learning. Sometimes a little complexity actually makes the models better,
Yeah.
more robust.
This is blowing my mind. But let's go back to that first question about human learning. We can learn from just one example. Can these analogizers do that too?
That's the really exciting part. Remember nearest neighbor. If you only have one example, you just find the closest thing to it, and that's your prediction. It just works that way. So like finding the best match, even if your library only has one book.
Exactly. And the possibilities are huge. Imagine mixing this with other stuff, like rule-based learning. You could make algorithms that learn from almost nothing. That would be huge for fields where data is hard to get.
Yeah, this is amazing. But are there any downsides to these analogizers? Nothing's perfect, right?
You're right. And a big challenge is this thing called the curse of dimensionality. It's like their kryptonite. Especially now with all this big data, think of it like trying to find your neighbor's house. But the city keeps growing into more and more dimensions. You just get lost and all the landmarks disappear.
Sounds like a data nightmare. How does this curse actually mess with the algorithms?
Basically, as you get more dimensions, you need way more data to fill the space. So all the unimportant stuff starts to hide the important stuff, and it gets hard to find similar examples.
So it's not just about more data. It's about the right data, knowing what actually matters.
Exactly. And this curse affects lots of algorithms. Like nearest neighbor and decision trees, they have trouble separating the good stuff from the noise in all those dimensions.
So knowing about this curse is important for picking the right tool and understanding what the results mean. It's like knowing what your tools can and can't do.
Exactly. And that's what researchers are working on now, finding ways to beat this curse and unlock the full power of analogizers.
This has been really eye-opening. We've seen how analogizers learn from similarity, the power of SVM, single example learning, and the challenges of this dimensionality thing.
It's a field that's moving fast with new discoveries all the time.
So where do we go from here? What's the future of analogizers? Are we close to machines that learn as easily as we do?
That's the big question, isn't it? And while we're not there yet, the progress is incredible. Imagine machines that can learn languages from a few conversations, or diagnose diseases from tiny clues in medical data, or even compose music by learning from every style out there.
Yeah, it's like something out of science fiction. But it all depends on us figuring out this analogy thing, how we connect the dots so easily.
Right, and that's what makes this whole thing so cool. It's not just about building super smart machines, it's about understanding ourselves. By looking at how machines learn from being similar, we learn about how our own brains work, how we make those connections and figure stuff out with just a little bit of information.
So it's like we're learning from the machines too.
Exactly. It's this back and forth between us and AI, each one pushing the other to learn more.
This deep dive has been a real trip. We've learned how analogizers work, their strengths and weaknesses, and how they could change everything.
Yeah, it's a field full of potential. But we gotta be careful, too. As we build these smarter and smarter analogizers, we gotta think about the ethics of it all. Make sure they're used for good,
Definitely.
Yeah.
So as we wrap this up, is there one big takeaway you want to leave us with, something to think about as we go back to our lives?
Well, I guess I'd say analogizers give us a peek into the future of machine learning, a future where machines learn not just from mountains of data, but from little patterns, unexpected links, even just one powerful example. Just like us, it's a future where the line between human and machine intelligence gets blurry. Makes us wonder what it really means to learn and understand and be intelligent.
Wow, that's deep. And for our listeners out there, if you're as fascinated by this as we are, go explore, learn more, maybe even get involved. Who knows? You might be the one to make the next big discovery in analogical reasoning.
And hey, if you enjoyed this journey into the world of analogizers, hit that like button, share this with your friends, and subscribe to The Deep Dive for more adventures into the unknown.
Until next time, stay curious and keep those connections flowing.